The firefighter on the right is preparing to raise this ladder. He pushes with a force F push straight upwards. He is positioned 3.5 meters from the butt of the ladder. The ladder is angled 30 degrees from the sidewalk. The ladder is 4 meters long and has a mass of 100 kilograms. What is the magnitude of the push force this firefighter exerts on the ladder? What is the magnitude of the normal force that the sidewalk exerts on the ladder? We may model the ladder as a uniform rod. Okay, so we see that this ladder is not rotating and it's not accelerating. So we can say that it's in equilibrium, which will mean that the net torque is equal to 0 and the net force is also equal to 0. So let's draw in these forces, and we see here straight upwards we have F push that this firefighter is exerting on the ladder. And then since we're modeling this ladder as a uniform rod, the weight force will be acting in the middle and it'll be straight down towards the center of the earth. So the ladder is angled 30 degrees to the sidewalk, and there will be one more force. There'll be normal force, and that'll be straight up. Let's try a better color here. All right, so that's normal force. So let's set up an expression for our net torque and see if we can use it to solve for F push. So we need to select our pivot point. I think the most useful one is going to be here, the butt of the ladder. So our expression will be net torque equals 0 equals the torque due to F push minus the torque due to weight. And we know this will be a positive torque because it would cause a counterclockwise rotation. And this will be a negative torque because it'll cause a clockwise rotation. And that is our convention. Now, will the normal force cause a torque? Well, I think it's going to be no. But let's put it in and so we can prove that to ourselves. So we can say plus torque due to normal. So again, we said our pivot point was here, the butt of the ladder, where the normal force is acting. So torque due to F push is going to equal R, which is the distance from where the force is acting to the pivot point, times the perpendicular component of F push, the component perpendicular to the rod, the ladder, minus torque of the weight will be R of the weight times the perpendicular component of the weight force. And now, if we try to figure out for normal, will be R of n times the perpendicular component of n. But we see that the R will be equal to 0 because this is at the pivot point. So this whole thing goes to 0. So we really could have just excluded it from our expression because it's acting at the pivot point. So what is this perpendicular component of our F push? It's not going to be our whole F push. It's just going to be the perpendicular component of this F push vector, as we can see here. So what is that? Well, we can use a trig function to find that out. So we know this angle is 30 degrees, and we can use cosine to find this adjacent component. So the perpendicular component of F push will equal cosine 30 F push. And now we want to do the same for our weight force. And so this will be the perpendicular component right here. And again, we can use a trig function, cosine, again, and that will be cosine 30 times weight will equal the perpendicular component. So that equals 0. So let's do some algebra. And figure out what our F push is equal to. Okay, so these cosine 30s will cancel out, and we'll see that RW times W over RF equals F push. So let's go back to the problem and see what those values are. So W, the weight is acting in the center of this uniform rod, and the rod is 4 meters long, so that's 2 meters. And the weight force, we know the mass is 100 kilograms, so m times g. So the weight force will be equal to 1,000 newtons. And we'll divide that by r sub f, and that's 3.5 meters. And so we get an F push equal to about 570 newtons. Okay, so we've solved the first part of the problem, but now we want to know what is the magnitude of the normal force that the sidewalk exerts on the ladder. So we can look back here when we made our claims about equilibrium. We see that F net is equal to 0. So if F net is equal to 0, then the sum of the forces in the x and y directions must be equal to 0. In this case, we're really just concerned with forces that are in the y direction. So we can say F net equals 0 equals F push minus weight plus normal. So F push we have determined to be 570 newtons. Weight we know to be 1,000 newtons. And normal. And so we can see that normal will equal 430 newtons.